Hi, in this video we're going to be looking at how we can use Monte Carlo methods in order to obtain numerical results and estimations by using random sampling. So here is a famous example of how to calculate pi using a Monte Carlo method. So the way it goes is you construct a square domain from 0 to 1 in both the x and y. You then generate random numbers uniformly between 0 and 1 for each of the x and y. You then evaluate whether those random numbers fall within this quarter circle. So using this equation, x squared plus y squared is less than 1. And we know that the area of this quarter circle is pi divided by 4. We know that the area of the overall domain is 1. And so the ratio of the points that fall within this quarter circle compared to the overall points that have been generated is pi by 4. And so an estimate for pi can be derived from this. So let's go to the top and have a look through. So in this video, we're going to have several examples. So the first one will be showing you this calculating of pi. The second one will be determining resulting distribution from a multivariate function with known distributions. And the third example will be estimating the noise of a measurement when the underlying probability is known. So before we get into this, we need to have a quick recap. I'm sure many people watching this video would be familiar with the idea of the mean and standard deviation. The mean is simply a formula that's given by this, in which you multiply the probability density function by x and then integrate it over all the domain. Or for a sample distribution, you simply sum up the probability of each occurrence times the variate of each occurrence. Likewise, the standard deviation is given by this formula, or for a sample distribution is given by this formula, and is a measure of how spread the data is. And the reason I've got this here as a recap is because we need to look at a couple of examples. So the first example here on the left are two probability distribution functions. One is for a normal distribution, the other is for a uniform distribution, as shown here. In this particular case, both of these distributions have the exact same mean and standard deviation. But what we can see here, that if we plot their cumulative distribution functions, they are completely different. So we see here that the probability as a function of the variate x is completely different for the two distributions, despite them having the same mean and standard deviation. And so from this, it is clear that the standard deviation is not defined by a fixed probability. So I think this is a common pitfall that people often make, is that when they talk about standard deviation, they may say standard deviation is where 68.27% of all the probability lies around the mean. That's not true. Standard deviation is not defined by this fixed probability. The standard deviation is defined by these formulae. This 68.27% value that people often quote is only specific for the normal distributions. Only if you know your data is normally distributed can you then make the claim that 68.27% of the data lies between -1 standard deviation and +1 standard deviation. So that's a very important point to remember going on, because there are plenty of formulas we can use that will propagate the standard deviation, but unless the underlying distribution is known, these formulas may give incorrect results when applying them to probability intervals, which we can see here. And in fact, in general, if we work out things like the mean, standard deviation or variance, skewness, kurtosis, etc., these are just the moments of a probability distribution, and you need progressively more of these moments to actually describe the distribution, which often isn't practical. So often when you're given a mean and standard deviation, you're told the distribution, or you know the distribution. So these are the two moments required to completely describe a normal distribution. And so in summary, the mean and standard deviation are not enough to fully describe a distribution. And just to give you another example, we have here the same normal distribution, and then we have a double normal distribution. So both of these distributions are probability distributions, they both integrate to 1. They both have the exact same mean and standard deviation, and yet again, their probability distributions are completely different. So if you were to naively say that 68% of the probability lies between -sigma and sigma, you would be wrong for this double normal distribution, like you would have been wrong for the uniform distribution. So that's very important to remember going forward. And this just becomes even more clear that the standard deviation is not defined by a fixed probability. And so what is a Monte Carlo method? So according to Wikipedia, there's no consensus on how a Monte Carlo should be defined, which both helps us and hinders us. But I think a good starting point to this is that a Monte Carlo method is a technique that can be used to solve a mathematical or statistical problem, and a Monte Carlo simulation uses repeated sampling to obtain statistical properties of some phenomenon. What does that mean? So we can go ahead and do our first example, which is the calculating of pi, which I discussed at the very beginning of the video. So the way we do this, again, as I said at the beginning of the video, we take a domain like this, from 0 to 1. We then generate pairs of uniform random numbers. Uniform random numbers are very easy to generate. Most computers have very efficient methods to generate these uniform random numbers or uniform pseudo-random numbers, but either way, they're uniformly distributed, so you have equal probability of getting a 0 all the way to a 1. So by generating these pairs of random numbers, placing them in the box here, and then finding the ones that are located inside this quarter circle, we can get our estimate for pi over 4, and likewise, timing this quantity by 4, we get our estimate for pi, and we can make a nice little animation showing this. Every time random numbers appear on the left, the estimate for pi is updated on the right. So in this case, the Monte Carlo method, they're using Monte Carlo simulation to estimate pi from random numbers. That's the method. And the simulation is generating these random pairs and then doing the comparison of whether it lies in this quarter circle. That's a very nice example of how a Monte Carlo method can be used. And it's quite remarkable that the value of pi can be estimated from random numbers as opposed to just formulas. And here's another example. If you do some statistical analysis, the overall question we're going to try and answer, what is the variation of our measured value? What does that mean? In this example, we have a voltage source, delivered as 5 volts. We then have a voltage divider formed by 2 resistors, R1 being 4.85 kilo ohm, and R2 being an NTC thermistor. Now an NTC thermistor is a thermistor in which the resistance changes with external temperature. So an NTC thermistor is often used as a thermometer. By measuring the resistance, you can calculate the temperature. And the way this works is that if you apply 5 volts here, then what happens is that voltage is divided by the ratio of these 2 resistors. So when the NTC, for example, is at 25 degrees, it will have a value of 10 kilo ohm. The value of voltage will then be 5 times 10 divided by, in brackets, 10 plus 4.85. That will be the value of voltage. Because we know this resistance here, we can calculate this resistance from the voltage measured and then calculate the temperature. Now the problem with this is that obviously we can measure voltage. Let's pretend we can measure the voltage perfectly. So measuring voltage to high accuracy is actually no problem. But the problem is that there is variation associated with this resistor here and the NTC itself. So even though it says it's 10 kilo ohm at 25 degrees Celsius, there will be some variation in the manufacturing process. Likewise, there is this quantity called beta. Beta describes how the resistance changes with temperature. This as well can vary. Even if 2 thermistors start out with the exact same resistance at the exact same temperature, the beta value in each one can change because of the material properties, meaning that when they both go to a new temperature, they may have a different value of resistance. So we've taken here an example of an amphenol, etc., thermistor, and it gives us in the data sheet that it has a beta value of 3936 plus or minus 1%, and a resistance at 25 degrees Celsius of 10 kilo ohm plus or minus 3%. Now on the top, we will apply a resistor of 4.85 kilo ohm with a variation of 5%. And so the question here, we have a thermistor in a voltage divider circuit. What is the error in measured temperature? Okay, so let's say we're measuring a temperature of 25 degrees, and this error will be due to the individual components we use. Because remember, we can measure voltage to a high degree of precision, and we're assuming that resistor 1 is this 4.85, and that the thermistor has these 2 properties. But in reality, if we made lots of these devices, these are going to vary, and we'll get a spread of both of these. And so when we measure a voltage here, we're going to be assuming these values. In reality, they can often be quite different, so we need to know what's the typical range of temperatures that we would calculate based on our measurement of voltage. And then going one further, we can say, if we then get the spread of temperatures that we would calculate after measuring voltage. What percentage of these devices would actually fall out of spec? And the spec here we'll define as being within plus or minus 1 degree Celsius of this 25 degrees. And this is important to note here, is that when it comes to these values from the datasheet, is that no information is given about what these errors are. So their distribution is unknown. And remember, as we said above, without knowing the distribution, you can't just go ahead and do probability intervals by using just, say, the mean and standard deviation. We need to know a lot more in order to be able to work out probability intervals. So this is where a pitfall could arise. So what we've done here is we've assumed that the errors listed here in the datasheets is plus or minus 1%, 3% and 5%. We're assuming that these errors are 3 sigmas from the mean, so 3 standard deviations from the mean. So using these 3 Gaussian distributions, these 3 normal distributions, we can go ahead and run a Monte Carlo simulation at 25 degrees Celsius. So we set the temperature equals 25 degrees. We generate a set of each one of these components, because remember, this is a random process. In the factory when these are made, it will pick up a resistor, it will pick up a thermistor, and both of those will be random. So just because one has a higher resistance doesn't mean the other one will. It could be random. It's random between the two. And that's what we're essentially doing. We're randomly sampling from our space. So we pick a random set from the thermistor, which includes its nominal resistance of 10k, its beta, and also pick a random resistor for our voltage divider. We then calculate the voltage across the NTC based on this random set. So based on this random component and this random component, we work out the voltage that we would expect to measure. We then calculate the temperature based on this. So remember, when we calculate the temperature, we're assuming this value and assuming these values. So we measure a voltage, assume these values, and then back calculate temperature. We then repeat steps 2 and 4 a large number of times. So this is where our large amount of random sampling comes in. So let's say we do it 50,000 times. Seems like a reasonable amount. Very easy for a computer to do. And then we can generate a histogram of the calculated temperatures. And this is what we get. So we see that from these 3 normal distributions, we end up, again, with another normal distribution, which is quite nice. We can work out the mean of this data, which is 25 degrees, and the standard deviation of this data, which is 0.44 degrees. We can then construct a normal curve based on this standard deviation and mean. And remember, the standard deviation and the mean is all you need to know to construct a normal distribution. So if your values are normally distributed, you just need the mean and standard deviation. And as we can see, there is an excellent fit between the two. As we started off with normal distributions, the function itself is quite simple, and we expect a normal distribution from this. We then go ahead and measure from our Monte Carlo simulation that 97.72% of these devices are within spec. So 97% of them are between 24 and 26 degrees. Because remember, we set the temperature to 25 degrees and then measured the spread of values we would expect based on the individual errors of the components. And likewise, if we use the normal distribution with these values that we got from the measured data, from this measured Monte Carlo data, we could also get the same value of 97.72% by using the CDF, the cumulative distribution function of the normal distribution, with these 2 values of 24 and 26. So in this case, they are normally distributed. Having normally distributed inputs of relatively simple functions often results in normally distributed results. But in general, calculating this resulting curve can actually be very difficult. So these 3 normal distributions here all go into a formula that describe the ratio of the resistances. So it's a ratio of normal distributions, which isn't a very nice calculation to do. And a common thing to do in error analysis is to calculate the mean and standard deviation using error propagation. So that rather than do a Monte Carlo simulation, we can use error propagation instead. So we can use maths instead of random numbers. But it does involve a large amount of maths, but is much simpler than calculating the final distribution. So to calculate the mean, we just use the formula evaluated at the mean. So we calculate the resistance of the divider, which we know, calculates the resistance of the NTC at a particular temperature, which we can calculate. We then go ahead and calculate a voltage based on that divider. We then back calculate what we think the resistance would be and what we think the temperature would be. And in this case, we get 25 because we're using the means here. Then when we back calculate, we also use this 4.85k and 10k, so we get 25. Now the interesting part is when we calculate the standard deviation, the square root of the variance for each of the parameters and functions, and we can add them according to this formula. So the propagation of variance says that the variance, standard deviation squared, of the resulting data, the resultant of the function is equal to the partial differentials of each component multiplied by the error associated with each one of those, or multiplied by the variance associated with each one of those. So in our particular example, we end up with these 4 equations that we need to calculate, and some of these are not nice to do mathematically, so you've got to think we've got quite a simple function of a voltage divider, and yet we've ended up with these quite nasty looking formulas. You can imagine these get a lot more complicated the more you do, but if we follow this process through, we get a value of 25 degrees for the mean and 0.44 for the standard deviation, which is exactly what we measured from our Monte Carlo results. And so in this case, we could have neglected the Monte Carlo step and just gone ahead and done error propagation instead. And so the summary from that is that the mean and standard deviation can be calculated analytically, and assuming a normal distribution, it does fit very well with the Monte Carlo distribution, with the Monte Carlo simulated distribution. And it also means that the yield can be estimated using the CDF of the normal distribution with the calculated mu and sigma, so that's calculated mean and standard deviation, which is not surprising. But what happens when we have a non-normally distributed variables? So for example, let's say that this plus or minus 1% of the beta is actually a uniform distribution. So maybe it's some process that's very flat, and they just chop off and say anything that falls without this plus or minus 1% can go. So think of this as an extreme practical case. So this is the sort of process that you might get in the sort of extreme where the manufacturer doesn't have a good process, and then they just have to bin most of their devices because of this. Likewise, for the nominal resistance at 25 degrees Celsius, we also have this plus or minus 3% around the mean here. Then the interesting one is that, so there's a very famous example of a resistor, so the distribution of a resistor. I think the quote was, "How do you think 5% resistors were made?" And it was insinuating that the resistors were made in bulk, so all resistors were made in bulk, and the manufacturer would pick out the middle 3%, and sell those as 3% resistors. They'd pick out the middle 1% from those and sell those as plus or minus 1% resistors, and then that leaves you at the end with these plus or minus 5% resistors. So you see here, you've got this very odd distribution where you've got the entire middle chunk missing because it's claimed that the manufacturer had measured them and then removed the ones that fall within 3%. And then what we do now is we run the Monte Carlo method again, so doing the same process before, but we see something completely different. So clearly, this distribution is not normally distributed, and we've estimated the yield here from the Monte Carlo data of 77.46%. Okay, so remember that 77.46% from the Monte Carlo data. And when we measure the standard deviation and the mean from this data, so from this Monte Carlo data, and then apply this to a normal distribution, we can see that if we are assuming a normal distribution, we'd be completely wrong. So it's not right to assume a normal distribution in this case. In fact, using a normal distribution from the measured mean and standard deviation would be completely wrong. And you have to remember, standard deviation and sigma are just 2 moments, and so do not completely describe any generic distribution. And let's actually go ahead and calculate, well, if we said how many of our devices are between 24 and 26 degrees based on the normal distribution, we would have gotten 81.56%. So in this case, we would have assumed we had a higher yield than we actually did. And that can cause a lot of problems, especially in industry. And again, what's interesting is that we can still do error propagation here. So we still didn't need to do the Monte Carlo simulation, because we could have said, let's use error propagation. So we can calculate the mean as before using the nominal values in the formulas. And we can also calculate the variance of the resulting function. And that's because the standard deviation of a uniform distribution is simply given by this formula. So it's the width divided by 2√3, width of the distribution. And again, this is because the mean and standard deviation are just formulas. They're not defined by fixed probabilities. They're simply a formula that is applied to the distribution. Following this math through again, so it's the exact same maths, because all this applies to the mean and standard deviation, so it doesn't take into account the distribution whatsoever. We end up with a value of 25 degrees plus or minus 0.7 for the standard deviation. Going back up to our curve, this is exactly what we got from measuring the Monte Carlo data. And so we can still calculate the mean and standard deviation analytically, that's absolutely no problem. However, again, just important to reiterate, these two values alone are not sufficient to describe the final distribution, hence estimations of yield are not possible. So I think this is a very important thing to remember. So just because we can do this analytically, so we can work out the mean, can work out the standard deviation of functions of random variables analytically, it doesn't mean that we can then use those two values to predict more things. So for example, predicting probability intervals, because we don't know their underlying distributions. So this highlights an important aspect of Monte Carlo simulation, is that if we know the underlying distributions, we can quite easily get the resulting distributions, whereas analytically, all we can do with calculating the mean and standard deviation is calculate the resulting mean and standard deviation, but not the resulting distribution. That's very, very important to remember. And so I think in summary, regardless of the individual distributions, a Monte Carlo analysis can generate the resulting distribution for any function, no matter how complicated the function is. It's simply a computational step for calculating that. Statistically generating the resulting distributions can be analytically impossible for even simple functions, particularly for non-normal distributions. This also really helps when you have distributions which have high covariance. So for example, if in this example, if the range of beta also depended on the range of resistance, doing that analytically is very, very difficult. And so the fallback approach there is definitely to be used in Monte Carlo simulation to do that. In this case, we've assumed all three are independent, so that, for example, beta and the resistance at 25 degrees can vary independently. But if that wasn't the case, it's very, very difficult. And the individual means and standard deviation can be used to calculate the resulting mean and resulting standard deviation, as discussed, using the formulas and propagation of variance. But it does not reveal the resulting distribution, leading to a common mistake when evaluating problems like this. So I've seen this lots of times, as someone calculates the mean and standard deviation of the resulting distribution of a series of inputs, and then goes ahead and calculates probability intervals. So saying that, 90% of our devices will lie between these two values. But there they've made the massive assumption that the resulting distribution is normally distributed, and that's sometimes not even the case for normally distributed inputs. You can have many inputs that are normally distributed, but then the way the function operates, so say you've got a lot of fractions, a lot of ratios, a lot of logs, for example, a lot of exponentials, the resulting distribution might not be normal. So even though you've worked out your mu and sigma from your error propagation, you've made the massive assumption at the end that the results were normally distributed. So in calculating your yield, you need to make sure that it is normally distributed. And this also highlights another fact, is that sometimes when a manufacturer gives you their plus or minus 3%, you don't know what that means. You don't know if it's uniform. You don't know if it's normally distributed at 3 sigma, at 5 sigma, at 6 sigma. All of those can make a massive difference to your resulting distribution. So the only way to truly know is if the manufacturer actually provide that information. So for example, in a lot of data sheets for electronic components, like op amps and things, you will see histograms of the typical, say, offset voltage on the input. So some manufacturers do this, but not all. And so the really only true way to know that would be to actually get samples and measure them. And now let's look at our final example. So this one's a bit different. So let's say you're running a long experiment that results in a relatively small number of observations. Running the experiment for longer isn't feasible or practical. So it might be an experiment where you have a very weak signal, or not a lot's actually happening over time, and you're just time constrained. So Monte Carlo simulation can be used to estimate the uncertainty of the measurement, provided the underlying mechanism is understood. So here is one where we know how the mechanism is formed, or have a good theory about what will happen. We then go ahead and measure something. We might not get a lot of data from that, so at least we know the underlying theory. And so sometimes this might be like a CCD array. A CCD array for example, in a vis spectrometer, detects the number of photons hitting the detector within a particular frequency, which is actually then binned. We can then go ahead and fit this data with a curve that describes the underlying mechanism. So we might know how our light source generates light, at what particular frequencies and what particular spread. We then get a measurement from our CCD array in which we have maybe a small number of events. So we have a lot of noise, we have a lot of shot noise, with either discrete events. So for example, we don't have anything between 1 and 0, or 1 and 2, because we either have 1, 2, 3, 4, as if you're measuring the individual photons. And measurements like this also apply to things like optical particle sizes, where you only measure whether a particle has actually appeared or not, and then bin it according to its size. You can't measure half a particle. It either has to happen or it doesn't. What we have here is we have some mock data that we've generated. So imagine this was data from a CCD array in blue. We can then go ahead and run a curve fitting algorithm in order to fit a curve to this data. And again, this curve comes from our knowledge of the light source itself. So we have a good knowledge about how this light source generates light. So all we now need to do is fit that particular type of curve with the data we've observed. Then we end up with a curve like this. And then go ahead and perform a Monte Carlo simulation. So what does this mean? In this particular case, if the measurement was performed over and over again, what would we expect to see? So it's taking the same number of events that occurred here. I think it's around 150 events that occurred. If you summed up all the bars here, 150. But if you were to do that measurement over and over again, based on this fit, remember this fit is a good theoretical prediction of what the light source is doing. Based on that, what would we expect to see? If I go ahead and play this, you can see that every time we ran this experiment again, we would expect to see something slightly different. And remember, the thing about this experiment is that we can't just keep running it over and over again. We're limited by time or something else that prevents us from just taking a large number of events. But you can see it varies quite a lot. And that's because we have this discrete nature of each of the events. We get what's called shot noise. And now we can go ahead and use this Monte Carlo simulation to generate the average histogram with error bars. And this should agree with the fit perfectly because we're generating the values based on this fit. So the way we do that is we use something called inverse transform sampling. I'll put a link in the description above to a video where I briefly touch on inverse transform sampling. But basically we generate random numbers based on this fitted distribution. So we get more of the hits around here where we have a higher peak. So we get our Monte Carlo average, which should agree perfectly with our fit because the fit was used to generate the random numbers for the Monte Carlo average. But the important information that we get here is that we get the standard deviation associated with each of these bins. So this is now quite important. So what's it telling us now is that by running the simulation over and over again with the same number of particles to which we have measured, using a distribution fit that we have a good theoretical understanding for, it means that we can generate an estimation of our standard deviation of each of these bins. And why is that important? So now we can use the information gained here, which is the standard deviation of each of those bins from our Monte Carlo simulation, and we can apply these standard deviations to the measured values, which is here. What we end up with here is our original histogram in blue. So this is our measured data, or our pretend measured data. Now have an estimation of the standard deviation from each of those bins. And if this is a good fit, and if we have estimated our standard deviation well, we should be able to plot a normalized residual plot. The fit is good. So let's have a look. So this is our normalized residual plot. And these residuals should follow a normal distribution if the fit is good. If we see any fanning out, that's a result of heteroskedasticity, which means that the underlying variance depends on this value of wavelength, which in this case there might be a bit of heteroskedasticity, but we could always go back and check for this with an appropriate test such as the Goldfeld quant test, which we won't do in this example, but it's something to look out for. And so moving on from this, so what did we actually do? So we took some data that we measured. It suffered from shot noise, so we didn't have a lot of samples for our data set, and the results were binned. but we did have a good understanding for the theoretical underlying process which generated those values. And so by using a Monte Carlo simulation, we asked the question, if we measured those same 130 events again, what's the typical variation that we would expect to see within each of those bins? We then use that information to generate our variance or standard deviation for each bin, which we could then apply back to our original data. We then checked whether those standard deviations formed a normal distribution in the standardized residual plot to show that the fit is indeed good. Then using this information, what could we do with it? Well, we could go back and ask the question, okay, let's pretend we could go back and say do the measurement for say twice as long. What would the benefit be? So we'd be able to go back, do the Monte Carlo simulation again, and we would see how these error bars change, and we'd then be able to determine whether doing this experiment for twice as long would be worth it. Because what we typically see is that these error bars would only change by 1 over root 2, so they wouldn't decrease in height as much as you would hope. And so it can be used as an important part of decision-making processes. And as well, this information can also be used in any future measurements. So say we did this experiment again for the same time, got roughly the same number of particles, we'd have a good estimate for the standard deviation. What are the advantages then of this Monte Carlo analysis? The Monte Carlo simulation allows one to quickly generate the resulting probability distribution for any combination of underlying probability distributions. It also allows for error estimation of small sample sizes if the underlying distribution is known or we have a good theoretical background of what causes it. A Monte Carlo simulation can also be performed with significantly less knowledge of advanced calculus and statistics. So some of the maths involved in generating distributions and error propagation requires some quite advanced knowledge of statistics and calculus. But a Monte Carlo simulation can be done by anyone really who understands basic calculus and statistics and knows how to program. And another good thing is that large numbers of simulations can be performed with even modest hardware. So even on laptops, you can be performing millions of simulations for these things to get your overall distributions. So I hope you found this video interesting. So that's where we'll leave it today. Hope we gained maybe just a little bit of information about what a Monte Carlo method is and how it can be used and what it can be used for. So thanks a lot.